Hello everyone, I hope you're having a great day as usual. In this video, we'll be looking at the Berkeley packet filter or the extended Berkeley packet filter and what it enables us to do with the Linux kernel. We'll get started right away with a little bit of the history with the Berkeley packet filter. The Berkeley packet filter had initially started as a way for us to define rules to whether to drop network packets. So this would either be on the router or on the firewall about which kind of packets you want to accept and which kind of packets you wish to drop straight away. One of the examples for this can be seen as it can be seen when you are using Wireshark, where you perform essentially filtering with the likes of TCP dot port equals 3306, for example. It's double equals. And similarly, you have the ip.adder check, which you can add for your IP address, which essentially lets you filter out IP addresses, or you can filter out your TCP traffic if you want to if you want to like take a look at one particular application's traffic. Anywho, so that's how the Berkeley packet filter had started initially, and it eventually made its way into the Linux kernel as well, where you could define such rules to drop packets on the kernel's networking stack. However, the extension came about in around 2014 into the Linux kernel, and this essentially allowed us to perform tracing in any part of the kernel. You can essentially add probes and whatnot. So the whole packet aspect of it has essentially been overridden. We don't really consider this a networking specific platform anymore. What the Berkeley packet filter allows you to do is it allows you to place trace points or probes in various parts of the kernel, whether that's your syscalls, whether that's your applications call stack, whether it's on networking events, and you essentially get a breakpoint at that point. So if you've used GDB or if you've used any sort of debugger, you would have placed breakpoints in your code at various places, and then you can like pause over there. You have the entire context of what various values, various variables hold, and you can make decisions based on that. So that's what the Berkeley packet filter allows you to do. If you've worked with Java, it's similar to aspect oriented programming, where you can essentially place place your own code, where you can inject your code at the beginning or the end of any random method that might be called. So let's take an example of uh, what you can achieve with the Berkeley packet filter. If you've worked with tracing utilities like Pixie or New Relic, that's what they use. They essentially, for example, when you're tracking how long it takes for you to form TCP connections, so there's a kernel syscall called kernel method called TCP underscore connect, and you essentially add breakpoints to the start and the end of this kernel method, and you can measure the time between these two events to actually calculate how long your TCP connections are taking, and that can be used as a tracing opportunity. Along with that, if you've worked with EKS or the Amazon Elastic Kubernetes service, they use a networking driver, the CNI called Cilium. I mean, they have their own version of it that's built on top of Cilium that actually uses the Berkeley eBPF as its way of performing the traffic forwarding for all of your uh, pods within your Kubernetes cluster. So the possibilities, as you can probably see, are endless. You can add probes, you can add breakpoints to any arbitrary point in your code as long as you can deterministically define where you want to place that probe. So what does that really mean? Like I gave the example with the TCP connect, you have a deterministic definition of where this method is so that you can place your probes in the beginning and the end of it. Similarly, if you're using libssl for libssl.so, you've got methods like ssl underscore write, and these are symbols that are published, that are exported by the libssl library. So you have deterministic positions of these in your call stack when you're running an application that uses libssl. So you know exactly where those methods start in the memory. And that's where you can add your own code, whether it's in the beginning or towards the end. So you can modify the logic as well in certain cases, depending on the kind of eBPF program you're writing. As a quick aside to what we've been talking about, if you're running containers, whether it's several containers that are running on your local machine, or if you've got a Kubernetes workload where you've got your worker node that's running your containers, they all share one common kernel. Since these containers don't run their own kernel, and the kernel belongs to the host machine, they all share one common kernel. And every time you add these probes, whether it's a trace point or a uprobe or a kprobe, all of these are handled by the kernel itself. So without actually having to deal with anything inside these containers, you will be able to add your tracing and your tracing capabilities by just making changes to the worker node. By just having one worker node run your eBPF application, you can look into the containers without having to add sidecars or any other overhead of such sort. So that's a pretty cool place where you can perform such kinds of tracing, especially in an environment where you don't even need to log into the container to add the tracing abilities. So what really, how how really is eBPF different from kernel programming? Well, if you're writing kernel modules, if you write, let's clear this up real quick actually. Right. So if we were to compare kernel modules with eBPF, one of the primary differences here is when it comes to a kernel module, if a kernel module was to crash, oh, that is bad, because a crashed kernel module will take down your entire kernel. It will essentially bring your entire machine to a halt. Whereas when it comes to eBPF, these applications are verified at runtime, and the kernel essentially makes sure that these applications will not crash. So when it comes to an eBPF application, there are certain conditions that your kernel space eBPF application has to meet. And those conditions are that it must terminate, it must terminate. So you cannot have an infinite loop, an unbounded infinite loop in there. And even if you do have a loop, you have to actually perform a loop unroll and whatnot to actually let the eBPF verifier actually verify your code. It can have a maximum of 1 million instructions. 1 million instructions, and instructions are not necessarily the same instructions that you would write in Rust or in C. These instructions are the actual assembly instructions in the eBPF assembly. So you have to make sure that all of your code is under all of your kernel space code. You can have user space code that can be as complicated as you want, but your kernel space code for one eBPF program has to be less than 1 million instructions. On top of that, you have a hard limit of 512 bytes on your stack. So you cannot have a stack that's larger than 512 bytes. There are ways to get around that with using various buffers and whatnot. We'll cover those as well in subsequent series, but for now, uh, these are the limitations that we need to care about. The advantage of these limitations, one more that I missed, is that you cannot have loops. So if you do want a loop, you have to essentially unroll your loop at compile time. We'll take a look at how that can be done in Rust, and there are multiple ways to do that in C using macros as well. Anywho, so what this essentially allows the Linux kernel to do is at runtime, it can verify for sure that your application is not going to crash. Your application is not going to just get stuck in an infinite loop, and it's not going to perform. There are certain checks it does that lets it perform any it essentially lets you check that you're not performing any memory unsafe operations. For example, you're not overfilling your buffers, or you're not checking, you're not oh, you're not dereferencing a pointer before you have checked whether it's null or not. And it also comes into play with the Turing halting problem. So if you've ever read about the Turing halting problem, the Turing halting problem essentially states that given an arbitrary piece of code, it is impossible. So it is impossible to determine to have a machine that, given an arbitrary piece of code, can predict whether an application will stop or it will keep going indefinitely. So there is a massive set of problems where you cannot definitively or deterministically assert that this application or this program is going to end at a certain point, or if it's going to keep going forever indefinitely. However, all of the eBPF applications have to satisfy this constraint where you can deterministically assert that these applications will in fact end at a certain point in time, and so that really limits the problem space that we have. And so there are certain conditions that we need to abide by because of these restrictions, but overall it does not really affect much because we try to keep our kernel space code as small as possible while maintaining that we maintain most of our business logic in our user space code. All right. So what are some of the places where you can place these breakpoints? Let's clear all of this real quick. Well, we've got kernel events. We've got network events. Got network events. Uh, Essentially lets you place these breakpoints whenever a packet comes in or the packet goes out. There's a cool thing called XDP in here, XDP, which is called the express data path, which essentially lets you place these breakpoints before the packet even comes into kernel memory, or essentially like the packet comes into the kernel stack where it goes through the entire kernel's handling, whether that's the TCP stack or the UDP stack or whatnot. So it comes in before that. So you could, for example, this is a very useful way to handle DDoS attacks, where you can drop packets before they even come into your before there's a lot of processing happening on your CPU. On top of that, certain network interface cards actually support offloading your XDP onto the NIC itself. So you can essentially drop the packet before it even comes into your CPU. Apart from that, you've got your kprobes. Kprobes. So kprobes are probes you can place in any kernel uh, in any kernel method, like before or after any kernel method, whether that's, for example, TCP connect or fopen or whatever syscall that your application might make, you can place it at that. Further, you've got uprobes. Uprobes. Uprobes are so an example of kprobes is the TCP connect method in the kernel. Connect. As for uprobes, you can have a uprobe at any point in a library or at any point that has a well-known symbol that is exposed. So for example, the example I had given earlier with OpenSSL, you've got libssl ssl.so that exposes ssl underscore write and ssl underscore read. So this allows you to essentially snoop in on SSL connections that are happening uh, on your kernel. Further, there's also the trace points. Trace points are points that are injected in the kernel itself. So one of the problems with kprobes is that a kprobe is a method. So it has no guarantees of backward compatibility. At some point in some kernel version, if the method definition changes, if the method prototype changes, your kprobe is going to stop working. The same thing applies with uprobes. If a version of the library changes the method definition, your uprobe is going to stop working. Similarly with trace points, uh, uh, sorry, as opposed to that with trace points are well-defined points that are in the kernel itself. They ensure backward and forward compatibility. So sorry, they ensure forward compatibility. So going forward, you don't need to worry about uh, the trace point actually stopping to work just because of a kernel upgrade. And an example of this trace point would be the start of your let's say execve. So execve is essentially a syscall that occurs when you start any application, whether that's curl, whether that's Firefox, whatever your Java application, whatever. That's one of the trace points that's one of the methods that gets called, and you have a trace point at that as well. So the trace point will essentially help you uh, trigger your eBPF program whenever it's called. So just so we're clear on this, the difference between a trace point and a kprobe is that a kprobe is on the actual source code of the kernel, so that is subject to change in future kernel versions. However, a trace point is uh, a defined trace point, a defined event that is emitted by the kernel itself. So the contract for the trace point is going to remain consistent with any kernel versions going forward. Let's go over the parts of the eBPF application or the entire stack that we'll be implementing. So you've got your eBPF code here. This is an eBPF binary. What needs to happen is we are going to have a user space application. So your eBPF code is going to run in the kernel, right? It's going to run in the kernel. We've got a user space application here. The user space application is going to load that into its own memory, and then it's going to perform a syscall that's called, I believe it's called the BPF syscall, and it's going to essentially feed this in, and that hands over our eBPF application to the kernel. The kernel is going to take that application, it's going to run the verifier on it. Then once the verifier checks pass, it's going to add that into our uh, into the kernel memory itself, and it's going to start running. A very good example of all of the flexibility eBPF allows you, or the amount of granularity it allows you, is demonstrated in an image I saw recently. Let me bring that up. So this image right here perfectly explains, it's from a blog post by Brendan Gregg. It perfectly explains just how much flexibility eBPF offers. So it's got essentially, it's just an illustration of just how much of the kernel the eBPF platform covers. You can pretty much add your probes anywhere you want, and that opens up an amazing number of possibilities when it comes to the kind of tracing that you can perform, the kind of security assessments that you can perform, and whatnot. I'll have a link to this blog post down in the video comments below as well. But anywho, let's get started with our Rust application and setting everything up. Right, so moving forward, let's take a look at why I keep referring to an eBPF program as something separate from your normal program. So eBPF is essentially a language of its own, not exactly a language, but I would call it an instruction set of its own. So this it runs as a virtual machine inside your kernel. So it's got its own instruction set, as opposed to an instruction set that you would run like x86, or you would have x86 64, or you would have ARM 64. You have a separate instruction set for eBPF applications. One slight aside here is that there's two different kinds of instruction sets, one for little endian and one for big endian machines, but let's ignore that for now. Anywho, so we've got this entirely different instruction set that your executable needs to be built in, that your binary needs to be built in. So how do we get this? Well, one option that we do have is using Clang. And this is the most widely used option. Clang is a LLVM compiler. So you've got your LLVM. LLVM is essentially a mapper for languages. So instead of having, for example, if you're creating your own language and you've got to write x86 assembly, x86 64, ARM 64, all of these different versions of assembly, instead of having a many to many mapping between your front end language and your back end language, back end being the raw assembly and the front end being the code that you and I understand, uh, what you can essentially do is, let's just call it any random lang. So let's just call it glang that you might be creating. Instead of having mappings for each of these separately, you can just create one mapping for LLVM, and then the LLVM compiler will take care of actually converting that into x86 or eBPF or ARM 64 assembly. So Clang is one of those front ends that lets you convert your C adjacent eBPF code into assembly. And similarly with Rust, we've got a tool chain that Aya provides us. Aya is a Rust library, and that essentially converts our eBPF application into LLVM, and then that LLVM and then the LLVM compiler can then convert that into eBPF code that we can then run on our Linux kernel. So let's take a look at how we can get started with all of this. One of the primary requirements of eBPF is that you need to use, especially when you're using it with, specifically, I mean, when you're using it with Rust, is that you need the nightly toolchain. The nightly toolchain, this essentially has the mappings that are required to actually convert your applications into binary. To get started, we'll take a look at the Aya Rust docs right away. And let's see if we can try getting a small eBPF program built real quick. So if you go into the getting started page of Aya, you've got a couple of instructions and you can essentially just follow them verbatim without any modifications, and it should work. It's fairly well documented. So we need to install the nightly Rust toolchain. I mean, obviously you need to have the stable Rust toolchain as well. Then you install the nightly Rust toolchain. You install a couple applications. So one of them is the Cargo BPF linker. Now I'm running on Linux x86 64, so I do not need to run this particular command. But if you're running Mac OS, or if you're running any other architecture, then you'll have to execute this command as well. And then after that, we can install cargo generate, which will help us in getting started with any eBPF applications real quick. All right, so once we've got all of that going, let's just copy the string that's in the documentation here and bring it over into our terminal. I'll go into the directory that I'm using here, and let's just paste that in. So as soon as you paste it, it's going to ask you for a project name. Let's just call it tutorial for now. Now here's where you decide which kind of an eBPF program you want to create. So in our particular case, we'll be creating a trace point just to get started, but we'll be covering a couple more samples, like for example, the U probes and the K probes as well later on down in the series. So let's create a trace point. Now it's going to ask you which kind of a trace point you want. And the best way to figure that out is you can go into sudo su into your essentially become the root user on your machine, and you can go into cd sys kernel debug tracing, and this is where you can get all of your syscalls. So if we, for example, if I was to go into I think it's called events, right? So in here, I've got all of the events that I can perform tracing over. Let's go into the syscalls folder. And in here, we've got a bunch of syscalls. In our particular scenario, we'll be taking a look at the connect syscall. The reason I'm going for the connect syscall is because it's fairly easy. If I was to look at something like the execve syscall, you would be seeing a lot of noise on the console. So just to make things easier, we're going to look at the connect syscall. So here we have sys enter connect and sys exit connect. So let's go into this folder as well, actually. Sys enter connect. Great. So now we're in this directory. Let me make this a little bigger. Okay. I can take a look at the format. This probably doesn't mean much at the moment, but we'll take a look at how we can understand all of this wall of text very soon. Anywho, so now let's just copy all of this over. The trace point name is going to be a syscall. Oh, sorry. Let me start all over again. The name is going to be tutorial. Right. So the name is going to be tutorial. It's going to be a trace point, and the type is going to be a sys interconnect. So a sys interconnect is when the connection syscall starts, and the sys exit connect would be when the syscall ends. Anyway, let's copy this over, and that is a syscall. Great. I think I have to change that to a syscall. That's fine. Let's just open this in Rust Rover and let's take a look at the code it has generated for us. Great. So as we can see, it has already generated. Oh, okay, my bad. I opened the wrong folder. So as you can see, it has created 3 folders for us. One is the tutorial folder. This is where your user space application is going to reside. This is where your application that deals with performing the syscalls and all of that is going to reside. We've got the common folder where you can have your common shared structures and whatnot. And we've got the tutorial eBPF, the eBPF folder, which is the eBPF part of our application. If you want to run this application, all you have to do is actually just run the script that's offered in the cargo run in the README. But let's take a look at all of the code that has automatically been generated for us. So if I go into the tutorial folder in the main Rust file, it has a lot of code, but and it might seem a little overwhelming, but most of the code at the top can just be skipped. You're essentially adding your resource limits and whatnot. It's really inconsequential. We're setting up the logging environment and all of that. What's really important for us is when we get into the eBPF part of the code, so we're essentially loading this program into our memory, into the user space memory. The This path is where the compiled eBPF binary is going to be placed. So we load that in, then we let the eBPF program know at what point they need to start the application. So I'll go over this part real quick in a few moments, but right after that it just lets the application we essentially let the eBPF platform know which syscall we're attaching the sys interconnect to, which syscall we're attaching our application to, and then after that it's just waiting for us to actually press Control C for exiting the application. Before we go over anything else, let's take a look at the eBPF program. So over on the left side, if we go into the tutorial-eBPF folder and we take a look at main.rs, so we're not doing much here. We've created a trace point here. This is a method, a function that essentially all it does is it logs that the trace point has been called, and that's all it's doing right now. So let's take a quick look at some of the links between the user space application and the kernel or the eBPF application. So what we've done is this right here. This is the name of the binary that's going to get generated. Then the part inside program mute, this is the function in the binary that's going to get called whenever the syscall is triggered. So for example, if I was to call this tutorial underscore func, then I would have to call this method right here, tutorial underscore func, right? Now that we've done all of that, let's take a quick look at actually running this application. I'm just going to copy the script they have over here. I can just click run and that should work. So it's going to take a while to compile the first time you do it. but it should be done pretty soon since this is a fairly limited eBPF application. Once it compiles, the eBPF application, the user space application has to be run as root because it needs to have certain capabilities to actually make the eBPF syscall. So it's going to ask you to, and let's do that real quick. Now it has given me an error. So let's take a look at what really happened. If you remember when we went over all of the files, this particular path is called syscalls, but I essentially skipped an S when I was writing it. So I need to add that S right here. Let's do that. And I can run my application again. Great. So I got this message that it's waiting for a control C. Let's open a terminal window and let's perform a curl to google.com. Yet we don't see anything. So what's really happening? This is something that had thrown me off for quite a while and it took me a long time, longer than I would like to admit to debug. So I wanted to make this point. Anywho, the way we fix that is the default logging context that your Rust application enters in is not defined here. So we need to define that. It's going to be Rust underscore log equals info, and then we can run this application. Now you can see the trace point is being called already. So this is probably some applications that are running in the background of my operating system that are making these calls. But I can just as easily perform a curl on google.com and I'll see it come up over here. So just to demonstrate this, let's get rid of all of my background tasks. And I think I'll keep OBS running. But apart from that, yeah, I think that's good enough. So let's make some space here. Let's clear our logs and then let's run this application once again. And every time I perform a curl to google.com, I should get this log. Great. So it's actually creating several connections under the wire. So I'm getting this trace point several times, but you get the gist. So far all we've done is actually just uh, sent out a logger whenever these syscalls occur, but very shortly down the line in the series we'll be checking the parameters that these methods are called with, or we'll be taking a look at extracting data from them and whatnot as well. So this is very exciting when it comes to performing security analysis, or for that matter, even if you want to do it for your own sake, if you're creating malware, for example, just as a purely learning opportunity. That's also a very interesting point to look into when it comes to using eBPF. Along with that, there's all obviously the networking aspect as well, where you can decide which packets you want to allow and which you want to deny. We'll be looking at that as well. So all in all, it's very exciting. I hope you've enjoyed this introductory video, and down the line we'll be taking a look at more complex applications and how we can develop them. Thanks for watching, and bye bye.